Okay, let's start. Hello everyone. Good afternoon. My name is Ajay Jacob, and I am the Director of Projects at the California Dreams Hub. Today, I have the honor to welcome Professor Puneet Gupta from UCLA to talk on scaled systems, design architecture, and pathfinding, scale-out chiplet-based systems, design architecture, and pathfinding. Professor Gupta received his B.Tech degree in electrical engineering from the Indian Institute of Technology, New Delhi. He did his Ph.D. from UC San Diego in 2007. He's currently in electrical engineering and electrical and computer engineering at UCLA. He co-founded Blaze DFM Incorporated in Sunnyvale and in 2004, and he served as its product architect until 2007. He has authored over 200 papers, 18 US patents, a book and 2 book chapters in the area of system technology co-optimization, as well as variability, reliability aware architectures. Professor Gupta is an IEEE Fellow and was a recipient of the NSF CAREER Award, the ACM SIGDA Outstanding New Faculty Award, SRC Inventor Recognition Award, and the IBM Faculty Award. And he currently leads the System Benchmarking Trust within the SRC JUMP 2.0 CHIME Packaging Center. So let's welcome Professor Puneet Gupta. The stage is yours.
Great. Thanks, Ajay. So I'm going to talk about some of the work we've been doing over the past few years on building large system using fine-grained, fine-pitch 2.5D integration and chiplets. And I'll start with an overview of why would we want to build such a system, sort of in the architectural context. Then we'll talk about a system that we have been trying to build. It's a fairly large, to the best of our knowledge, the largest that we know of. Designing, taping it out, and the challenges in that. And then eventually I'll end with how do you do the so-called system technology co-optimization or pathfinding of technologies and the architectures together for such systems and technologies, right? So that's the focus. And if there are any questions, please just feel free to interrupt me. I'll prefer to take the questions as the talk goes rather than all the questions towards the end of the talk. So before I talk about designing systems, let me put what the context is. So let me first define what I call as advanced packaging or advanced integration in this case. And this is a nice plot from one of my colleagues, Subbu Iyer, and where the plot shows how the packaging dimensions have scaled over the decades compared to on-chip dimensions. And what this is highlighting is how the on-chip dimensions have scaled far, far more than packaging dimensions. And only over the last few years, this trend is kind of little bit normalizing, where the packaging dimensions are starting to scale in a comparable fashion, right? And this era is what we typically refer to as advanced packaging, advanced integration, etc., where suddenly we are talking about chiplets, where we're talking about very intimately connected chips over a substrate. And this is all being enabled by essentially very fine pitch packaging at close proximity. And the end goal of something like this is to shrink the gap between what is on chip and what is off chip interconnect. It simplifies inter-chip signaling. It makes high performance multi-chip systems even viable. This could be 2.5D, which will be the focus of my talk today, but it could be potentially 3D as well. And it also allows for heterogeneity in terms of mixing and matching technologies within the same substrate. So what does this sort of advanced integration buy us? One big thing it buys us is heterogeneity. I can literally have various generations of CMOS technologies, non-CMOS technologies, tailored towards memories, tailored towards logic, tailored toward network interfaces, etc., all tightly connected on the same substrate, right? And this could be even enabling completely new power delivery mechanisms, etc., with this, and connectivity mechanisms as well, right? A kind of corollary to this is it allows you to do selective upgrades to the system IPs without respinning the entire system from scratch. And that has some advantages as well, cost and kind of turnaround time at the very least. The second big advantage, which is what I'm going to focus more on today, is it allows one to build very large systems without bad yield concerns, right? Because what we're talking about is small chiplets integrated over a large substrate, and that large substrate becomes my large system. It has the possibility to go well beyond the reticle size, which is again going to be the focus today, so-called, let's say, wafer scale. And this talk will be addressing the challenges of such chiplet-based scale-out systems. And this scale-out or scale-up is already happening, right? We have, in context of chiplets, we went from a single die 800 millimeter square rod SoC to 1.5x reticle size packages, to 2x reticle size packages, to now 3x reticle size packages, which are commercially available, very near future 5 to 6x, and eventually the 50x wafer scale, with some companies even showing that as well. So what are these wafer scale processors? That's these, as the name suggests, it is the processors that span a full silicon wafer, which means in case of a 100 millimeter wafer, it's about 8,000 millimeter square, all the way up to a 300 millimeter wafer, which can be as much as 70,000 millimeter square, right? And just by comparison, the largest single system on chip that you can build today is about 800 millimeters square. So what does it buy you? The biggest thing it buys us is cheaper and faster inter-chip interconnect. So on the right, you see this plot of a kind of rough analysis of what is the energy per bit of communication when the signals are on chip, between packages on a PCB, between multiple boards in a kind of a racks type system, or on a single wafer with, let's call it, wafer scale interconnect. And what WSI or wafer scale interconnect does, it comes very close to what on-chip wiring would look like, almost the same, right? And it's much less energy hungry, much lower latency compared to inter-package or inter-node interconnect. And why may one want it? Because this demand for compute has unfortunately been scaling way faster than Moore's law, largely being driven by machine learning, especially these large language models. And on the right, you see a picture of how the black line is showing the so-called Moore's law scaling over the last decade or so. And then the blue line is showing kind of the more vision style language or vision style machine learning models, which were already scaling faster than Moore's law. And the green line is showing the scaling of compute in these so-called large language models, which are scaling way faster than the black line Moore's law. Right? So the demand for compute is just increasing way faster than available compute on a single die. And that's what is incentivizing building larger and larger packages or larger and larger systems, which are tightly connected to each other. And the challenge in building such systems is, over the decades, our fabrication, our packaging, our design, our architecture, test, every single thing has been tailored to serve a system on chip at best, which is 800 millimeters square. So when I talk about wafer scale integration, for us, it basically boils down to taking small known good chiplets and bonding them to a passive interconnect only wafer. So the passive wafer has only copper wiring, maybe 2 to 6 layers of copper wiring. And then these small known good chiplets are bonded at fine pitch onto the silicon substrate, and then they're connected at fine pitch on standard silicon copper wiring on silicon as well. So my colleague Subbu Iyer has developed a whole process, and he has, I think, given a talk earlier about the fine pitch bonding. And So they have demonstrated down to 10 micron pitch thermal compression bonding, with the chiplets being separated by order 100 microns or so, right? And that's the context that my work builds upon. So to motivate this case, let's first do a kind of a analysis on a scaled up system of a GPU, right? Imagine if I wanted to build a massive GPU. I mean, if you look at NVIDIA's annual GPU announcement, they seem to be already inching towards this direction, where now there are two GPUs in a single package, which are connected on a so-called HGX or a DGX box with very, very high bandwidth interconnect. And so we say, let's push it to the end limit. Let's say, what if I build a whole wafer full of just GPUs, right? And they are very tightly connected to each other. And what would it entail? So let's first look at the good parts, right? So this is a little bit older study. So the numbers are not completely up to date, but they're in the right ballpark. So it's, let's say I have a GPU with two HBM stacks surrounding it. So the GPU die is about 500 millimeters square. The DRAM die is about 100 millimeters square each. So your total kind of module area becomes about 700 millimeters square, right? So GPU die power is about 200 watts or so. Each HBM stack's power is about 35 watts. So that gives me, again, the module power to be about 270 watts, right? And if all I did was pack these GPUs on a 300 millimeter wafer as much as I can, you can do the arithmetic, but it will boil down to about 72 total GPU modules that I can pack onto a single silicon wafer. And that sounds very, very impressive, right? 72 GPUs on a single silicon wafer is more than a rack worth of GPUs, right? So that's sounds very, very impressive if we can pull it off. Now, can we actually build it? Right? There are three major constraints, physical constraints, which kind of unfortunately stop us from building it as is. First is thermal. So this Waferscale GPU, if each module consumes 300 watts, you have 70 odd modules, you're talking about 20 plus kilowatts of power on a 50, 60,000 millimeter square substrate, right? That's fairly high power density. And you need some way to extract that heat. So that's the thermal issue. Let's say the thermal issue was solvable. Equally complicated, if not worse, issue is how do you deliver this much power to the wafer itself? So 20 kilowatts of power, if I deliver it at 1 volt, it's 20 kiloamps. I mean, getting 20 kiloamps of current into the wafer would be like almost impossible. So you'll have to have something where you might have to deliver the current at high voltages and do point of load conversion to lower voltages and what is the overhead of that, etc. Right? The third thing is, okay, I packed these GPUs, but it is pointless if these GPUs are just sitting by themselves, right? The whole point of putting them onto a wafer was that I will connect them densely at very high bandwidths. And so you need to decide a network which connects them at very high bandwidths. And what should be that network topology, which is plausible here, right? The substrate, the packaging technology that we've been using is this so-called silicon interconnect fabric, which is essentially a full thickness silicon wafer. And for the time being, analysis is done assuming it has up to 4 metal layers, right? So you can increase the number of metal layers, but there's a downside of cost and yield with that comes with it. So we started off with 72, right? And if I look at what can I cool with nothing too fancy, it's essentially a dual-sided air cooling because it's a full thickness silicon substrate. So we kind of little bit optimistically assume that you can get airflow from the top surface as well as the bottom surface because silicon is a decent conductor of heat. And so that improves your total burnable power somewhat by about 50 to 70%. So even with that, all you can cool is about 34 GPUs, right? If you say, I'm going to deliver current to it, then all I can power up is about 24 GPUs. right? So we're down from 72 to 24 already, if I account for thermal and power delivery constraints, right? So we can play some tricks because of the nature of GPUs and the nature of typical workloads that are run on GPUs, where they tend to be relatively balanced, and we can use this somewhat well-known technique called voltage stacking, where think of it as a resistive ladder style power delivery network. And with that, you can, and with little bit of operating the GPU slower, you can you can put up to 40 GPUs, which you can deliver current to and cool down as well, right? So we're down from 72 to 40 using the nature of GPUs, which tend to be relatively workload balanced. So then the next question becomes, how do I connect them? We explored a bunch of different network topologies, from a straightforward mesh to a 1D torus to a 2D torus. And with the number of wires that are needed, you can roughly estimate what the full wafer yield would be just for the interconnect wafer, the passive wafer. And then we said that, okay, the one that makes sense is a simple mesh interconnect, because that guarantees us reasonable yield and still decent bandwidth, with some restrictions on what the network topology can be. It is a straightforward mesh. Now, how well does this work? So now you have two alternative kind of Waferscale GPU floor plans, right? One is a 24 GPU floor plan, which does not use voltage stacking, in which case, effectively, every GPU module has its own voltage regulator, decoupling cap, etc., and that adds a substantial amount of overhead, silicon overhead, to do that, because I mean VRMs will typically need large passives, and that takes up area. If you do voltage stacking, you can reduce this kind of power delivery overhead substantially by about 3 to 4x. And that allows you to pack about 40 GPUs. So those are the two cases. The 24 GPU case, in terms of software workloads, is completely flexible. 40 GPU case has little bit of scheduling constraints, because within a stack, you want the workloads to be well matched. Okay. How much does this buy us? So to compare, what we did is we compared it against a multi-package massive PCB, right? So we said, okay, if I want to build a 40 GPU system out of conventional packaging, then maybe I can put 4 GPUs on one massive package, and then construct a massive PCB with 10 of these packages, right? That is likely not possible, but think of it as a thought experiment, right? Even with that, what you get is about 5x better performance and about 22x better energy delay product across a variety of GPU benchmarks, comparing this multi-chip package plus PCB system to a Waferscale integrated system. Right? So that is the driving motivation about why do we even bother building such massive scale-out chiplet-based systems, right? You're talking about 20x energy efficiency and as much as 5x sheer performance improvement, right? So with that kind of as a architectural motivation, let's jump into trying to build one. So at UCLA, few years back, we started on this project of trying to build a Waferscale system. Now, of course, we are not going to build a Waferscale GPU burning 20 kilowatts at the university. So we changed the architecture a little bit to serve a slightly different purpose. So this is more intended for accelerating random graph type applications, where they tend to be more memory dominated, and the compute is relatively simple for most of these applications. So in this case, the architecture was essentially taking small making a processor chiplet with 14 low power ARM cores in it. So that is one processor chiplet. Then there is a memory chiplet, which in our case is basically standard SRAM. So you get every tile takes 2 chiplets, and the goal is to to kind of have 1,000 such tiles on a 200 millimeter wafer scale substrate. Right. So the exact specs, you can read it on the side. The chiplets themselves are taped out in TSMC N40, and on the bottom right picture, you can see our current state of assembly. So you can kind of see the test harness board, and the zoom out is the silicon substrate. This is not an interposer. I will clarify that. It's a full thickness silicon substrate with 8 chiplets bonded on it, with at 10 micron pitch, with inter-chiplet separation being 100 microns. Right? And this is what we have tested so far, and we are slowly building up to the full-scale system. Now, so now let me talk about what are the different issues that we faced in taping out and designing this system. And I'm actually going to focus squarely on design challenges. There is a whole spectrum of packaging or assembly challenges that I'm not going to talk about. But I'll focus on the design aspects of it. So the first is, how should we deliver power to all these chiplets across the wafer, right? So even though we use a low power system, everything is low power, still we burn about a kilowatt or so, right? And on a 200 millimeter substrate, wafer substrate. So we still have a problem of delivering power to these 2,000 chiplets, right? Somehow. Now, you can imagine a variety of ways of delivering power, right? You could deliver the power from the front side or the top side. You could deliver the power from the back side by using, let's say, through wafer vias. In our case, when we taped it out, at that point, the substrate did not support through wafer vias. So we decided on a wasteful but simple scheme, which is we will deliver power from the edges at 2.5 volts. And then there will be a small LDO at every chip, which will down convert it to 1 volt. And yes, there is substantial amount of power delivery losses in the scheme. But in our case, simplicity of implementation was very, very important. Now, the other challenge we faced is, okay, we could deliver power, right? But now any chip that is towards the center of the wafer is several centimeters away from the nearest high quality capacitor, right? This is not the case in conventional packages, which are small, because within the package, you will have decaps. Then at the board right next to the package, you will have a bunch of decaps, which will ensure good quality power delivery. In our case, the board is a centimeter plus away. So several centimeters away. So those capacitors are not that useful. So as a result, when we tape this out, the silicon substrate that we were working with, that did not support any built-in capacitors in them. So as a result, about a third of our die area is just decaps in this, just to do good power delivery, right? Oh, now after that, there've been improvements where the substrates can support high quality caps, dense caps as well. So then after we solve the power delivery issue, the next issue is, how do I distribute clock over 15,000 millimeters square, right? All of us have trouble distributing clock over 300-400 millimeter square chips, right? How do you distribute it over 15,000 millimeters square, right? And here, there are several issues. The first issue is that typically you would have a PLL on die. The PLL will need a stable voltage reference that will generate clock from a slow master clock, and that's what is supplying the chip. distributing a stable voltage reference to 2000 chips over a 15,000 millimeters squared substrate did not sound like a good idea for us. So what we decided was that we will put the PLL only on one of the edge chips, which is closest to the edge, activate the PLL only on that will generate a high frequency clock, and then distribute the high frequency clock over the entire wafer, right? And the additional losses, etc., are very small because, as I said, the inter-chiplet separation for us is just about 100 microns. So the additional parasitics for that is not a big deal. Right? Then, if you're distributing such a clock over such a long area, you can have the clock effectively die down because of PN mismatches. Right? This happens even on large single SoCs, but we have this problem on steroids. So there are special circuitry introduced in every chip to kind of correct the duty cycle distortion, and also we invert the clock at every hop as well. So the neighboring chips operate on different phases of the clock. And on top of that, we do neighboring die communicate over not fully synchronous interfaces, just to make sure things go okay. So even after that, let's say we can distribute clocks. The next problem we face with clocking is, what if one of the chips dies or it doesn't get bonded correctly, right? If you distribute it as a just like that, then that will disconnect a big swath of the clock distribution. So for us, our clocking itself is done as a fault-tolerant mesh. So every chip receives clock from its 4 neighbors and effectively does a majority vote. And if it finds any one of them as active, then that clock is sourced as the main clock for that specific chip. So the chances of clock dying down, therefore, are dramatically reduced because all your 4 neighbors will need to be failing for clock to not reach you. So that is dealing with just the clocking part of it, right? How do I test such a chip? Right? This is a die photo of the compute chiplet. And on the bottom right, with that orange oval, what you can see is the fine pitch pads. These are 10 micron pitch, right? And they're essentially impossible to probe. So if I can't probe anything, how do I test a chiplet before I bond it? And what we did was, now which has become a relatively standard approach, is we replicated a very tiny fraction of these pads as large sacrificial pads, right, which are shown as on the right. And these are primarily some JTAG signals, some clock, VDD, ground, few important signals which are replicated on these large pitch pads as well, which can be probed in conventional fashion before bonding. And these pads are actually never bonded. These are purely sacrificial. They're actually not bonded at all. They're only for test purposes. And this allows us to do some basic kind of known good die testing before we bond the part. Okay, so we did pre-bond, some basic pre-bond known good die testing, but that still doesn't guarantee that things will work. Maybe the bonding might fail, maybe the chip itself, we didn't test it well enough. And now if the chiplets fail, now the question is how do I make sure every chip can still communicate with every other chip if some chips in the middle are failing? And for that, the network on this wafer was designed in a fault-tolerant fashion. So we use some thing called dimension order routing, which is an XY routing. And so the way the routing scheme was designed is that between every pair of chiplets, there are 2 routes that can connect to them. And this allows a fair degree of fault tolerance in the network. And on the right, you can see what fraction of total paths are disconnected with and without this fault tolerance. So red is if you even get on this wafer 5 faulty chips, about 12% of pairs of chips cannot talk to each other anymore, right? But with this fault tolerance, that percentage drops from 12 to about 2, right? So that is far, far more manageable. Okay. So that is a kind of a quick summary of a variety of architecture as well as design challenges that we faced in designing these wafer scale systems. Right. One thing I forgot to mention here is since our bonding was 10 micron pitch, standard foundry provided IOs were completely useless for us. Right. They are designed for 75, 100, 150 micron pitches. Right. So, and they're designed to drive data over several millimeters. While in our case, we wanted to drive data over half a millimeter at worst. While we were constrained to the IO fitting within a 10 micron pitch footprint. There was also thing about we were fairly confident that we are not going to face electrostatic discharge or ESD problems, which are anywhere close to what packaged parts face. So we had to dramatically simplify the ESD protection circuitry so that it does not add a massive amount of load on the IOs and the footprint as well. So the IOs were basically a custom designed, much simpler IOs actually. They are essentially simple cascaded buffers with very basic ESD diode style protection. But they fit within the 10 micron footprint. Yet another challenge that I didn't talk about is the more sort of EDA side of it, that if you're trying to build a design with 15,000 millimeters square, you take any commercial EDA physical design tool, try to load it, the design in, and try to say route it. It'll not go anywhere. So we had, even though you know that the routing problem is actually very simple, much simpler than what the tools are used to handle, but the extent of the substrate causes the problems. And so we had to have our custom routers implemented just to route this interchiplet wiring. So that was kind of the architectural motivation and example design that we have done with the scale out Waferscale chiplet-based systems. And now I'm going to jump into the third aspect, which is how do I do the so-called system technology co-optimization or pathfinding for such systems and technologies? So before I do that, I want to take a quick break to see if there are any questions.
I do have a question. Is there any question online? There are no questions online. I do have one question, Puneet.
Sure.
So the question that I have is in your slide 12. So in the slide 12, so you say this is not an interposer. Essentially, this is you are putting this on a silicon wafer, but you are still creating some kind of a silicon bridge underneath. So
no, there's no silicon bridge.
Oh, in the next slide you show the silicon bridge.
No, there's no silicon bridge. This is just wiring.
So how do you do this? How do you do this wiring?
No, this is on silicon wafer. It is vanilla silicon wafer, full thickness, whatever, 700 microns odd thick silicon wafer. And there's normal copper wiring on it, 4 layers of copper wiring.
4 layers of copper wiring is on top of the silicon.
Just regular silicon, just like you do process silicon chips.
I got it. I mean, this is just like regular silicon. When you mean by regular silicon is back end of line silicon.
Yeah, just back end of line silicon. Exactly.
Yeah. So why would you not call it an interposer? Because an interposer would be a passive. And how do you differentiate between an interposer versus a silicon?
Interposer by definition interposes between two things. Typically it interposes between the chip and the package. Right? Here, there is no package laminate below this. This is it.
Okay.
Right? There is no package laminate below it. This is it. You cannot make wafer scale systems if you use a quote unquote interposer, because interposers will need to be thinned down because you want to make TSVs through it. And if you thin down, it is nearly impossible to make like a 15,000 millimeters square substrate.
Okay. Got it. I mean, Yes. So then the next question would be that let's assume if you compare this with a TSV-based interposer, what would be the energy product budget?
No, the TSV-based interposer, you cannot scale to a wafer. You just can't. Right? Because as soon as you add TSVs, unless you make TSVs massive, you'll be thinning it down. Thinning it down to, I don't know,
It's a 30 micrometers or
30,
50
40,
micrometers.
whatever, 50 micron
Yeah.
thickness, right?
Yes.
And
Yeah.
while a full thickness silicon wafer is 700 microns, right?
Yes.
So,
Yes.
right. So if you thin it down that much, it is very difficult to make it as big. It's just like fragile. Let's
Okay. Okay.
right? So I don't. You can't. It's very difficult to. I mean, that's why in the stitch interposer kind of setups, they move very slowly from 1x to 1.5x to 2x to 2.5x size, reticle size, right? They're not going to 50x that quickly.
Okay. So in this part, so TSVs do have advantage because because the interconnect distance is much less compared to
No.
long range interconnect.
No.
One point. The long range interconnect, we are thinking about having a Waferscale integration, right? So there is interconnect delay you would expect if you go beyond certain distance on the wafer.
Yeah, so I think what you're saying is no, but the TSV doesn't add any value there, right? The TSV are primarily used in the interposer to dig through the interposer and connect to the package, right? And
Power lines,
for power or whatever else, so that you can go outside the package, right?
Yes, that is power lines, but you can also have interposers. TSVs for other power.
Yeah, you can have it, and so anything that you would want the organic laminate to do something with, then yes, TSVs can be useful in that context, right?
Okay.
Here, there is no organic laminate below this, right? This is silicon. So even if you want to do long range signaling, there are a couple of options. One is what we did here, which is long range signaling is done through kind of thoroughfare or feed throughs through the chiplets, right? So we buffer it through the chiplets and then send it along to the next chiplet. So that's how the long range signaling is done in this one. You could make RF style long links. You could make long range electrical links, copper links as well on the silicon wafer. Yes, it is a bit more lossy, but it is definitely doable as well.
Because one of the study that I did some time ago, it's quite some time ago, on 22 FD-SOI, we figured out that if you want the long range interconnect below 4 millimeter, then it is going to be lossy.
Yeah.
So any chip that you can that you're interconnecting below 4 millimeter, because then it is the optical interconnect that will actually help you out in long range, is what I studied. But anyway.
I mean, yes,
there are other questions as well.
Yes. So I think there's a question from David Shaw that is an assumption of known good die are used. So known good die is a very strong word. So I would say that the assumption is probably good die are used, and way we do it is by that simple scheme of testing, kind of very straightforward testing that we do here. This by no means can guarantee that these die are really, really known good, but there is some basic testing to do, like make sure that completely dead chiplets are not bonded. Okay, I think there's another question. The recorded version will be available. I think Amy is going to post that at some point. And from Shripriya, so if we are not doing SRAM, but doing DRAM, in principle, nothing much changes, because for us, we treat the SRAM chiplet as a chiplet. The only challenge is going to be, I mean, for us, we could not use DRAM. The main reason is DRAM fabrication is not easily accessible at the university. And we will need a custom fabrication because we are using a 10 micron pitch bumping here. So that was a big driving reason of why we could not do DRAM. Here, TSMC was very helpful. They did some custom backend processing for us so that we could demonstrate this fine pitch bonding.
Okay, thanks, Puneet.
Sure. Is there any more questions? Okay.
There is one more question which is asking for power loss in Waferscale integration.
So the power loss is actually very high. In our current this edge power delivery scheme, the power loss is very, very high. I don't have the exact number on top of my head, but we decided just to simplify the design, we will bear the power loss. This is not a 10 kilowatt system. It is still just about a 1 kilowatt system. So power losses are high. I'm guessing, if I recall correctly, they're upwards of 15-20%. So the power losses are definitely high, but by doing this simplified edge delivery, it makes it design much easier.
Okay, thanks. I was probably more referring to the power losses, the interconnect side. Is that the same?
Oh no, I was talking power losses when delivering power itself.
Okay. I get. Yeah.
You could deliver power from the backside through wafer vias,
Right.
but that has processing issues. So that's why we decided here just to do edge power delivery, which is design-wise simpler, but losses-wise not so great.
Okay. Thank you.
Yeah, Ben, I think you have a question.
Yeah, sorry I joined late. You
Yeah.
might have already talked about this. Have you considered the optical clock distribution?
No. So this is vanilla silicon. There is no photonics in this right now, and the clock distribution. To be honest, yes, we haven't considered optical or resonant clocking or any of those other kind of more sophisticated clocking schemes.
Okay, so in your scheme, you have these 4 neighbors working with the central one. That seems to create some latency. Are there some accumulation of latency? Whereas when you do optical clock distribution, you can have all the n squared diodes get the same optical clock at the same time.
Yeah, so I think yes. So the skew in the electrical clocking is very difficult to handle. So that's why our interfaces are not synchronous from chiplet to chiplet. So they're mesosynchronous. So we are fairly immune to at least small skew problems. Yes, if the skew is massive, then it's a problem. But small skew problems, it's not a big deal, at least in this architecture.
All right, good. And then in our center, we do this gallium nitride-based power. We talked about kilowatt, so that the high voltage will help you, because if you have low current, high voltage, it destroys power, but the ohmic voltage drop will be less.
Yes. No. All of this, I completely agree. But here, just remember one thing in back of our mind is we have to fabricate this in commercial technology. We have to do the assembly in a university clean room and make it work. Right? So a lot of the choices are also driven by that.
Okay.
And this was taped out nearly 3-4 years back. So don't compare it with what is done today.
Yeah. Okay, one last thing. You talked about 10 micron being challenging and so on. So the hybrid bonding DBI allows you to go 8 micron, 10 micron, and sub-micron as well. Yeah. But that's might be but it's expensive. Yeah.
Yeah. So this is thermal compression bonding, and it is, as far as I know, even today, 10 micron pitch is pretty much state of the art for thermal compression bonding. Hybrid bonding can go fine, you're right. But hybrid bonding has other issues. That's a sidetrack discussion, but
that's right. You have to get the wafer form delivery. Yes, it's expensive. All right, thanks a lot.
Sure. I don't think I missed anything. Yeah. Okay. So
I think you can continue.
Let me move on to the so-called pathfinding or the STCO aspects a little bit as well. So I talked about architecture. I talked about design, and let's assume that there is an incentive to build such large chiplet-based systems. And let's assume that we will be able to figure out the design methodology issues and EDA tooling issues to be able to build them. So then the next question becomes, what should you build and what do you want from the technology, which would be valuable, right? So this, and here I'm going to narrow the scope to one workload, which is training of large neural network models, right? And that's a perfectly valid narrowing because that's what is driving most of technology development and architecture development in hardware today. And so that itself has a large hardware architecture space, that has a large software parallelism space, and of course it has a large technology choice space as well, whether it's memory technology, packaging technology, logic technology, networking technology, et cetera, et cetera, et cetera. So how do I reason about all of this together in a consistent fashion? And that's been one of our goals in the last few years, to build this sort of self-consistent kind of materials to software type pathfinding framework. I'm going to talk about a component of that, or two components of that framework today. And it's an ongoing work. So every passing few months, there is a small improvement on what we are able to do there. And the framework I'm going to talk about is what we call as deep flow. It's a system technology co-optimization framework where the architecture is something that looks like a machine learning accelerator, maybe like a GPU. So you could somewhat fairly flexibly tune what that microarchitecture of the GPU system looks like, how many HBMs around it, how many compute units are there within the die, what is the level 2 cache, what is the network within the chip, what is the network within the package, what is the package to package network, et cetera, right? So all of these can be tuned. You can tune the things like bump patches. You can tune things like if you want to try out different memory technologies. All of that is tunable in the so-called architectural description within this framework called deep flow. The second part it models well beyond the architecture and the hardware, it models the software parallelization. And this is absolutely critical for especially machine learning, large distributed machine learning workloads, because there are lots and lots of clever parallelization techniques that have been developed over the last 10 years, which very carefully orchestrate how a machine learning model is split up and distributed over tens, hundreds, thousands of nodes, right? And if that part is not modeled correctly, it's essentially garbage in, garbage out for any STCO pathfinding framework for machine learning. So deep flow models the three most popular types of parallelization techniques. Data parallel, which is essentially keeps the model everywhere but splits the training data. Layer parallel or pipeline parallel, which splits the model sequentially one layer at a time. And kernel parallel, which essentially takes your large matrix multiply that you're going to do matrix in there, and then you chop it up into small matrix multiplies and distribute them. Right? But these are the three most popular parallelization techniques, and all three are modeled in here. And it does some basic analysis of how to distribute things, where to put each parallel node depending on the connectivity, and then estimates the total execution time, including the network time. How well does this work? So we compared and benchmarked it against running the same workload on actual NVIDIA hardware. So ranging from 2 generation of GPUs, V100 and P4, and a BGX box, which had 8 V100 GPUs on it. So leftmost side, you see this scatter plot of validating different sizes of matrix multiplies or gems. And there are like thousands of points there. And the error is for large GPU clusters is less than 5-6% or so, which is very good for a modeling tool. And the rightmost side is doing the same thing, but on a LSTM style large language model. And there also the error is fairly small. So remember, the comparison is NVIDIA software pipeline, NVIDIA hardware running the exact same code as deep flow. That's the comparison point. So there are a lot of things which are unknown to us in terms of modeling, especially in the software stack of NVIDIA. And some of that, this error is largely coming from there. So then we've done a lot of, once you have the framework working and it's reasonably reliable, there's no end to what kind of what if analysis you can do with it. So here are some example what if analysis. Some of it was done in a joint work with IMEC as well. So on the bottom bar plots, you see 3 case studies of saying, if I did GPT-3 7.5 billion training, that LLM model, over 1,000 GPUs, right? That's the use case here, right? 1,000 GPU rack system, and I'm doing model training of this somewhat large language model, and then I'm going to look at whether I am memory bound or compute bound. What fraction of your time goes in memory and what memory accesses and what fraction of your time goes in compute flops, right? So we start off with N12 because V100 was designed in N12 process. And in N12, you are almost completely compute bound, right? So so there is not improving memory is not that valuable, right? But now, as soon as you start scaling the logic technology node down, by the time of N5, it's a 50-50 split. By the time of N3, you're completely memory bound. Compute has no role to play with HBM2. Now that you can get a little bit of relief by moving from HBM2 to HBM3, and then further relief moving from HBM3 to the projected HBM4. And this is just showing that. On the top right, you see a more elaborate plot, which shows if I take this system and the same model training and scale logic technology from N12 all the way to a projected N1, take HBM technology from HBM2 to HBM3 to projected HBM4, take the rack scale network from InfiniBand of different generations from 100 gigabyte per second to 200 gigabyte per second to 400 gigabyte per second, and then say, how does my execution time improve? At every point, the bottleneck may be different, right? In some of these points, HBM or the memory bandwidth is the bottleneck. Some of these points, the network bandwidth is the bottleneck. Some of these points, maybe the internal L2 bandwidth may be the bottleneck. So the bottlenecks are different for each of these points. But what you can see as a whole is improving one thing is obviously not going to cut it here, right? The network needs to improve. Connectivity to the memory needs to improve. The memory capacity needs to improve. And of course, the compute needs to track it as well. So that was performance analysis of deep flow. The other aspect of advanced packaging is the cost, right? One of the driving motivations of advanced packaging has always been around, it will reduce cost because I'm building smaller chiplets, they yield better, et cetera, et cetera, et cetera. So to argue it, to make that argument more thoroughly, we built a pretty elaborate system description and system cost model for chiplets, which models assembly technology, the wafer processing technology, the IOs, the test processes, and now slowly power and thermal as well, in one consistent framework, which we call as SCATch. The model, those of you who want to use it, both deep flow and the SCATch model are freely available on GitHub. But what it does is it essentially takes all of this, allows you to define an arbitrarily complicated 2.5D or 3D stacked system, and then essentially propagates cost all through the stack to estimate the total system cost, right? So you can define an arbitrarily complicated system. It has built-in yield models, built-in cost models, built-in area models, etc. For each of these, and now built-in test models as well. And it allows you to change any of those parameters and predict the overall system cost in it. Okay. So here's an example, for example, of how test is modeled, just to give an idea of what happens, right? So for the test case, each chiplet is assumed to have a true yield, which is coming from the process. There is a tested yield, which is basically saying there is a true yield, but depending on the quality of the known good die testing, there will be test escapes. So before bonding, I only have certain degree of confidence. So I have a tested yield. I don't know the true yield, right? True yield is going to be lower than the tested yield, right? And so now test escapes will go through, they will be bonded and stacked, and then they will be eventually discovered at the later system level test, right? And then these test escapes will cause other die to be thrown away along with them because of the stacking, right? So this whole sequence is modeled to predict the total system cost and total system yield. So you can change things like test quality for different chiplets to different ways. You can change stacking order. You can change whether you're mid-bond testing or not, pre-bond testing, how quality, what is the test, do you test the interposer or not, etc., etc., etc. Within this framework. Here again, 2 example case studies. The left one was done again with IMEC, where they had an internal system and we wanted to do an analysis of cost performance in terms of STCO, right? So kind of like a performance per watt per dollar for their systems. And there we were interested in 4 alternative implementations of the same systems, right? You have one massive SoC plus HBM. You have one massive 3D stack plus HBM. You can have a couple of small 3D stacks stitched on an interposer, or you could have a bunch of a large interposer with a bunch of chips, including HBMs on it, right? So 4 alternative configurations ranging from an extreme SoC case to an extreme 3D case. And the goal was to compare the performance between them and the cost. And the performance here is a workload level performance, right? This is not frequency. This is not just that. It is actually running an actual workload. It was some sparse matrix multiply in this example. And the workload simulator was with IMEC. And this is just showing that if I start building larger systems, then 3D starts looking more and more attractive, right? So it depends on the scale of the system itself that you're trying to build, right? One or the other will give you a better flops per dollar per watt. The right side is an interesting study that we had done, which is saying if I take a homogeneous large tiled array of processors and 800 millimeter square processor and try to chop it up into smaller and smaller chiplets and connect them together, right? How would the cost scale as I keep chopping it into smaller and smaller chunks? And the interesting conclusion out of the study was that if I cared about cost, it will be very difficult to justify really small chiplets, right? So the sort of the cost optimal chiplet size is somewhere between 10 and 40 millimeter square or so, right? Because if you make it much larger, then the chiplet yield starts to matter. If you make it much smaller, then the assembly cost starts to shoot up. So the sweet spot is somewhere in this kind of 10 to 50 odd millimeter square. The exact number will depend on a variety of factors. But that's what at least this study showed. And just to summarize, what we want to say is this large-scale chiplet-based processing is here to stay, and we need to develop whole new design methodologies to deal with the problems which are, some of them are old problems, but much more severe when you talk about large scale, and some of them are somewhat newer problems itself. And STCO framework, as I said, is critical for doing many of these studies. Great.
Thank you, Puneet.
Okay, sorry I took a little
No,
bit over.
it was indeed a great talk. Thank you so very much.
Sure.
And lots of information we have bundled into some few slides. That's good. Any more questions here? Okay, I think people are starting to leave because it's 4 past.
Sure.
Amy, you could post your presentation. Amy? Oh, Amy is okay, started sharing. Oh, it's still coming up? Okay, great. Okay, so and once again, Puneet, thank you very much. And this is this slide essentially. If you are interested in registering, please register such that you get the technical information in your email. Next slide, Amy. And our next in the seminar series next week, it is Julia Greed from Caltech who is going to give us this talk. And thank you all for attending today, and see you next week.
Thank you.
Thank you, Puneet.
Bye.
Bye.